All right. Good morning, everybody. Just plugging the speaker in here, getting it to. There we go. Speaker should be working now. Speaker and microphone, that is. I was going to try the include commuter audio thing and just have it be that, pick up audio that way, but I didn't want to jinx having it not work. What do I have here? Kira, David, Sarah, Caitlin, Paige. Oh, there's Kayla. All right. So Dawson and Margot so far. All right. Here we go. Kayla, you're gonna need to go a little farther away. I can hear my echo. It's kind of weird. All right. All right. So continuing our journey through the nature of light, wave, and particle properties. Any questions so far? No? All right. So we're going to look at a couple different things today, gravity and how it affects light, light and to do with conservation of momentum properties that we've talked about recently, refraction, which is review. So there's some questions about Snell's law and things like that as you know, calculation practice from previous work. And I guess it's you didn't see much of it in grade 10. So anyways, maybe it's not totally just review. So we're looking at motion of light to start it with here, and to do with particles, of course. One of the things here is Newton's gonna, I was gonna say, of course, because Newton, there's something to do with Newton here, but coming up, but I'm talking about Einstein stuff first. So Einstein developed general relativity, his theory of general relativity, which came about from, he did special relativity first, which we're going to study in detail in this course, which is weird effects to do with just non-accelerated motion, uniform motion, and the fact that light has a speed that is the same relative to any observer. So when we get to that unit, I'll be talking about how if something to do with speed relative to any observer is weird, then that impacts all the things to do with speed. So distance and time, of course, are to do with speed. And so if something's weird to do with speed, that means there must be something weird to do with distance and time. That's what we're going to be looking at. And then also speed has to do with momentum. And so momentum has to do with mass. And so things that are weird to do with speed have something, there's something weird to do with mass as well. That's special relativity. He went on after that to talk about general relativity, which we've actually talked a little bit about. We talked about how if you're completely freely falling, you're not actually feeling a force of gravity, and that's kind of weird. But it turns out the reason for that is because being in a gravitational field and accelerating are actually sort of the same effect. So you could be in a spaceship right now that'd be accelerating up at 9.8 meters per second squared, and it would feel the same as experiencing gravity as we are right now. And there's a really good reason for that. It's because they're literally actually the same thing. It's kind of weird, but true. So the way we're traveling through space-time is the same as if we were accelerating. Anyways, that's what general relativity is about. And so as part of his work to do with general relativity, I should maybe say one more thing. Special relativity said that if you're inside of a constant moving spaceship, there's no experiment you could do to determine, you know, if you're really moving or not. All experiments would be the same if you have constant velocity of 0 or constant velocity of any number relative to anything. The general relativity equivalence principle would be that if you're inside of an object and inside of a house like you are right now, there's no experiment you could do to determine whether or not you're experiencing gravity forces or whether you're experiencing what we could call non-inertial reference frame acceleration forces, right? If you're in a spaceship that's accelerating up, you wouldn't be able to actually determine that just with internal experiments. you have to look out a window to see what's really going on. So that's the equivalence principle for general relativity that he worked out. And so he predicted, as part of his general relativity, finally getting to this, that light was affected by gravity, right? And so, you know, think of that as kind of seems like pretty good evidence in favor of particle nature of light, I guess, right? That it's attracted by gravity. He went on to advise astronomers that during a solar eclipse, when it got really dark, a star that normally would be viewed as here would come along here, light would come along from the star like this. Let me just do this, right? Light's coming from the star like this, coming along. It's going to be purple there to match, but anyways, and it deflects, it changes direction because of gravity, right? So it gets attracted due to gravity. Yeah, so let's say attracted to the sun's mass, which is, you know, we're saying it's affected by gravity. Anyways, so now the direction of it is like this, and just like we saw in our optics unit in grade 10, if light looks like it came from, you know, it came in this direction, then I should go based on that arrow there, I guess, right? But if light looks like it came from that direction, we use a big arrow here like that, so it's obvious, right? If light looks like it came like that, then your eyes, you know, get tricked into thinking the star is here. So it's like the observed position during the eclipse. So it's this change in the position. That Einstein predicted. Astronomers went and checked and looked and measured, and not only was it deflected as he said, it was deflected by the exact amount that he predicted. Okay, so light is affected by gravity, just like particles with mass. Okay, so I'm going to, I was just going to grab like this page that's down here that I've been talking about that I'm going to always keep referring back to. I saw it just a second ago. That particle or mass, it's same as the one on the previous page here. I just want to dedicate a page to it. Like basically at this point, let's do this. You know, certainly seems like we're saying here, right? Just I said it up there in the paragraph anyways, but it's like, yeah, just to emphasize. Yeah, so what was the next part here? Light's attracted by gravity. Yeah, I'll do the wave version here too. So we know that in terms of particles and motion and so on, that the universal wave equation works for light. So we have, you know, the frequency of light and the wavelength of light, and so light clearly has wave properties as well, and so we've got evidence of wave nature of light as well, right? So the beat goes on here. It just, you're going to see this for a little while. So now we're saying, you know, wave nature of light apparently here is very obvious as well. You did a bunch of calculations from the previous lesson. There was questions assigned to do with v equals f lambda, and it's all about wave properties of light. And so we're talking about particle properties of light and wave particles properties of light. Sorry, that all are making sense, all are working. So, you know, back to this light affected by gravity thing. So how much more particle-ish can you get, right? So then what's the mass of the particle of light? You know, is it zero? Is it, you know, so let me click on this video first to do with that. You've seen this one before, I think.
McCain Super Fries, golden,
a second here.
Fries versus everything.
We're all familiar with gravity as the reason objects fall, but there's much, much more to gravity than that.
So there were, when you saw this before, there's parts of this video that was kind of like, ooh, some kind of far out there, and we're kind of reaching that far out location.
Gravity is a long-range attractive force between all objects with mass. It's what keeps us from falling off the Earth, it's what keeps the Earth in orbit around the Sun, and it's what caused the Sun itself to form 4.5 billion years ago. It's amazing to think that every massive object attracts every other in the universe. That means that your dog, the Earth, and a black hole in the Andromeda Galaxy 2.5 million light years away are all gravitationally attracted to you, and you to them. In the 17th century, Isaac Newton discovered that the strength of the gravitational force decreases by the square of the distance between two objects. So if you're twice as far away, gravity is only 1/4 as strong. He also discovered that the strength of gravity is proportional to the mass of the objects in question. The more massive an object, the stronger the gravitational force. That's why we can all feel the Earth pulling on us, but don't really notice the pull of the moon. It's smaller and farther away. The moon's gravity is strong enough to cause the tides, though. And when I said earlier that gravity is an attraction between objects with mass, I lied. I meant objects with energy. Because in addition to massive objects, gravity also attracts light and other massless but energetic particles, so that a photon of light can be bent slightly passing the sun or trapped completely by a black hole. Now do you understand the gravity of the situation?
Ha ha ha. All right, so that's a reminder of things you've seen long ago. So basically, it turns out that gravity can attract mass and also energy, and so light doesn't have to have mass in order to be attracted by gravity. It has energy, and so that's affected by gravity too. And so the gravity attracts energy business. There's a connection between energy and mass, is what Einstein worked out as E equals mc squared. So C is that proportionality constant between energy and mass. Is that C, the speed of light, is what the speed of light is, right? So 3.0 or 300 million meters per second is a proportionality constant, just like all the other proportionality constants we found, like resistance between voltage and current and so on and so on. Okay, that speed of light is actually very determinable based on measurements to do with mass and the equivalent energy. Weird, wild stuff. That's where I talk about the mass of an electron is 9.11 times 10 to the negative 31 kilograms, or 0.511 mega electron volts. So the kilograms version is the mass version. The mega electron volt version is the energy version. It's literally the energy equivalent to 9.11 times 10 to the negative 31. So let's keep going. If light is made of particles, then maybe it can reflect and so on. And so we can consider the law of conservation of momentum. So in room 124, there's a little toy thing here called a radiometer. And so when you turn light on, like strong light next to it, this thing will actually spin. This little set of metal vanes, they call them, but little metal, rectangles, little squares diagonally attached to the middle there. It's free to spin on top of this pin, and it's trapped inside this dome here that presumably has like a decent people think it has a vacuum in there. We'll see. Anyways, so what happens? Well, if you look at this, if you look at the momentum consideration here, we got the black side absorbs light and the white side reflects light, right? Just based on our knowledge of light properties and so on. So let's just run through the numbers for this. If you're absorbing, then light's coming in with a speed here. The initial speed of the main is 0, right? Then we have the final velocities. Because it's absorbing, we get one of these deals going on where we've got a final combined velocity like that. So based on the absorption effect, we're predicting this as the final velocity. And then based on the reflection property, we're going to have a lot of the same stuff here. We're going to have initial velocity of light coming in, 0 velocity of the metal sheet or whatever at first or whatever. And so now this is different, right? Because we're not absorbing. So now we're going to say, okay, well, this V1 prime is going to be the speed of light the other way. So it's going to be a negative value, right? Because it's reflecting. So that's what I'm saying. Light's coming in as a positive V1, going out as a negative V1 prime. So let's look at the values here and say, okay, well, if we solve for V2 prime, we get this. Now, remember I said this thing's negative, right? So we're subtracting that from both sides, which means we're subtracting a negative, which means we're adding a number, okay? So in this case, we've got M1V1 divided by M1 plus M2. In this case, we've got M1V1 plus some extra stuff, only divided by M2. can you tell which one leads to a greater final velocity? The black side or the white side? So we've got the M1, V1 in both sides, right? Picture even without. Go ahead.
I was going to say the white side because it'll be smaller on the denominator.
Exactly. So that's a good analysis to start with, right? As whereas like we're dividing by bigger stuff here, making it a smaller result, right? So that's automatically smaller result. And then on top of that, we got both factors we have that are different from the black to the white side here. Both factors lead to this one being the bigger one. Right? So we can just basically just say, okay, well then we've got the idea of large number over a smaller number, right? What we just analyzed here. So it should rotate based on conservation of momentum. This is a bigger velocity, so basically sort of add the effect of the two changes in velocities, and you get that it should go so that the white side trails, right? And so this was analyzed. This device was created for this purpose, to look at conservation of momentum to do with light. And so the story goes that they did the calculations, are like, okay, so it should go. And so they built the thing, they turned the light on, and it started spinning, and they cheered and started planning on publishing their papers and getting their Nobel Prize. Until they noticed something about this. So this is the radiometer in room 124. And so there it is, just sitting back up a second here, right? So they're just sitting stationary. There's the light bulb from my little mystery circuit thing. And so we're going to flick the light on. And it spins. Yay, oh my gosh, we just proved conservation of momentum. What an amazing thing. We're going to support Newton's particle theory of light, right? But then after a little while, people look at it, and what do you notice about how it spins? Is it going so that the white side is trailing? Do it again here. See it right there? It's spinning so that the black side is trailing, right? It's spinning the wrong way. So you watch the video. Does it spin? Yeah, it does, right? But does that confirm conservation of momentum? Do with particles of light? No, right? It actually spins the wrong way. So it's not a conservation of momentum effect. So you're like, oh darn, it doesn't do what momentum should. So we're not actually observing conservation of momentum and the resulting spin to do with it, right? Instead, it actually spins due to heat. What happens is inside of this thing, it's not a perfect vacuum, because perfect vacuums are hard to achieve, and this thing was like $10 at a science store. Like, it's not a super expensive device, but there is a low pressure in there so that it can spin easily, but there is still molecules of air in there. Those molecules of air at the black surface heat up more, and so they start to bounce around more, right? So the air molecules start to vibrate and so on, and they smash into the black side way more often because they're vibrating more, and they kick it, they make it move, they push on it. And so when it's spinning, it actually ends up spinning this way, like this, right? Where the molecules on this side are vibrating back and forth and hitting that black surface, kicking it to turn that way. View it as clockwise from above. This is the way it actually goes, clockwise, above, right? Ends up going clockwise from above, and I feel like maybe I should just copy and paste this stuff onto the conclusion page and leave this page alone. Yeah, I'll put that on there. Group, shrink. Right, it ends up going clockwise from above, which is totally the wrong way. So the party ended, and their scientists were sad to realize they weren't going to get a Nobel Prize for confirming that light has momentum. Kind of funny, right? So that's the story to do with that on record there. So keeping going. oh, I should mention that light does have momentum, but it's we'll look at it later on. Light does have momentum. I'm gonna say like stay tuned. We're gonna see it later on. It's just certainly not discovered as part of this device. Yeah, so yeah. There we go. Anyway, so refraction, a familiar one, right? Refraction from grade 10 stuff. We talked about, an object coming in, and this is a little demonstration device. I'm not sure if I think I did show it, but if we have light coming in a slow speed material, and then it speeds up, this little ramp can kind of illustrate the idea of it, like it refracts, changes the angle that it's coming in at based on it sliding down the hill and its speed changing and so on. But so the prediction, if we're going from slow to fast, would be that the refraction would go towards the normal, because it's going to go like down the hill. Like you'd have to see it in person maybe to see it, but better. But the way it rolls down the hill, it ends up rolling towards the normal, and so we get refraction towards the normal. So the angle of incidence would be greater than the angle of refraction. So that would be basically Newton's prediction for particle refraction directions based on particle analysis, going from a slow to a fast material. If you are remembering the finger and the thumb trick and so on, though, maybe you're bringing your finger and thumb in together, your thumb on the bottom and you're right here and your finger on the top. Your thumb's going to get to the fast material. It's going to get ahead, right? And so our prediction for waves would be that it would refract away from the normal, right? So that's the finger and thumb, or the wagon wheels or whatever. This is going to get faster velocity as we go into the fast. So wave analysis predicts that it would go away from the normal, okay? So basically at that point, you'd go and you'd test light itself, and you'd see that light, of course, refracts away from the normal. That's what we did, right? We actually used light in our analysis already in grade 10, of course. This wasn't known back then because speeds of light weren't known in materials. So I guess maybe Newton must have thought that light speeds up when it goes through light. Yeah, you could rationalize that, I'm sure, right? You'd be like, oh, there's particles to grip onto and get a boost or something, instead of it being reality that the particles cause things to slow down. I talked about how the energy of the light gets transferred from molecule to molecule, right? And it takes a little while to do that, so it slows it down. So this one seems very much like the wave wins, of course, because that's what light is really doing, right? So, all along here, we're putting little question marks saying, so it's a wave, right? So it's like, yeah, it does it. So does that mean light's a wave? Well, keep going, right? Keep studying, because we have some things that seem like particles, and some things, especially the gravity one, right? So we are going to include a review, or just work specifically to do with refraction itself as well. So that's more of a review page, but I'll get to the details of the calculations in a second. Here, that's my screen. Once it lets me control my screen again here. Yeah, there we go. My scribbles. Oh, that's just, again, that's the review stuff in grade 10. So basically, if we're going from slow to fast, what's true about the angle of incidence, right? So picture going from slow to fast. And if we had light coming in like this, it's at an angle here of incidence, what's going to happen? Is it going to refract towards or away from that? Well, we're going in, and my top finger gets in the fast first, so it moves down and away, and so it actually goes like that, right? So you could say the angle of refraction would be bigger. It'd be the statement to do with this, right? The angle of refraction would be bigger than the angle of incidence. So angle of refraction bigger than angle of incidence. Okay, so we've got the video analysis of the idea of fingers and thumbs, or even if you did like a set of wheels here, right? Set of wheels coming in, this wheel's in the fast first, right? So wheel in the fast. Fast velocity first, gets ahead. Nice little analogy to help us make good predictions. I'm not suggesting light is actually a set of wheels or fingers and thumbs. It's just a scientific model. Helps us predict and understand things, or feel like we understand at least. When light is traveling from glass to air, what eventually happens to light once the angle of incidence gets big enough? Do you remember what the name, the angle that it causes 90 degrees is called? So let's redo this.
Total internal reflection? Is that what it was?
Got it. Total internal reflection. That's right. I think you said it there close enough, right? So basically, as we go farther and farther along here, eventually this one goes all the way to there. And so if we had a ray of light coming in like that, that refracted all right along there, and this made this angle of refraction equal to 90 degrees, then it leads to instead, this can't happen, instead it reflects. Okay, so that is total internal reflection. Absolutely, good job, Sarah. Total internal reflection. So just going over a lot of the ideas that we've talked about, right? What happens to the amount of refraction when you increase the index of refraction? Well, obviously, if you increase the index of refraction, you're going to increase the amount of refraction. That's easier. So that this angle here was referred to as the critical angle. It's an angle of interest, basically, right? If you want to know how big does the angle need to be in order to make reflection happen, because you need reflection to happen for the device you're designing, you know, you need to be able to figure out what the angle needs to be and then design the geometry of your binoculars or your microscope or telescope or whatever you're building, whatever optical device you're building, and using total internal reflection. That's part of it. All right. Find angle instance. What happens to angle reflection is increasing angle instance. Oh, this is these questions lead to this page here. So basically, if you're looking at the relationship between the angle of incidence and the angle of refraction, you have a bunch of pairs of numbers, and you're looking to see, like, I don't know, is one half as big as the other? Is one twice as big as the other? Is one the root of the other? Like, there's some kind of mathematical relationship here, right? Math relationship, what we're looking for to be able to figure out that property. And when you look through that, it's actually kind of a tricky one. I don't often do this as an activity in a class because it's pretty rough to try and get it. But you know, you'd be graphing things and you're looking for a straight line, right? Is what you really want. So you want this straight line. And spoiler alert here, this is what leads to it. Sine of angle I and sine of angle R graphed gives you a straight line. So then, you know, that tells you that sine of angle I is proportional to sine of angle R, and so the proportionality constant is some value that has to do with the physical situation, right? It's the determining factor between the two, and so it's the physical property of the material that is determining how much bending, how much refraction occurs, and so that's what we call our index of refraction. So that's that. So we have this starting. This is how we got that formula originally, right? That index of refraction equals sine angle I over sine angle R. I'm just going to steal this from here, down here as well. Oopsie daisy. Undo that. Right, so I don't have that happening. Yeah, that's what index refraction is equal to. That's the grade 10 version of index refraction that we've seen. some index of refraction. If you're looking for a vacuum, or like, the ones that are most familiar, of course, is like water and air, right? So I would underline those ones, maybe like water 1.33, diamond 2.42. You might remember that glass was like 1.51 or 1.52 or something like that. These are just the ratios of those signs of the angles of incidence and refraction. A true vacuum is 1, because we're actually comparing to the speed in a vacuum, right? Air is basically 1, but it's not quite 1, of course. Air has a little bit of a refraction effect on the direction of light. So when light comes into the atmosphere, it actually does refract a little bit, and that causes optical illusions you've seen before, to do with like the shape of the sun and things like that, because there is some refraction of the atmosphere. So the light changes direction, then where something appears to be changes, right? The usual stuff from the optics unit. So as seen in grade 10, we have this stuff like we just looked at. And I feel like I could box this up a little bit first, but that's just what we just saw. So the next step for us in grade 12, when we move on and learn some more about this, is to realize that that's not really just the index of refraction for glass or water or whatever. It's actually both of the index of refractions combined. So you'd actually have the index of refraction of, if you're going from air to glass. So we have air to glass here. Then this is in the refractive material. This is the glass. Index refraction for glass divided by the index refraction for air, right? But remember, this number here is, pretty much 1, right? So I'm going to do a squiggly line and say it's pretty much a 1, right? And so that's why we got away with saying that it was just the index refraction of glass. Truly, it's actually the ratio of both the indexes of refraction. So this is actually a 1 here, approximately, right? So that's why that approximation worked. It says in that little paragraph there. So if you want, you can write index of refraction like that, like Snell's law like that. I'm not actually gonna use that one as much. People like it because then the I's are together and the R's are together and it just feels nice. But on the next page, I'm going to show you the one that we use way more. Okay. So you certainly can still write this down. I would write this one down for sure. The purple saying index refraction of glass, index refraction of air is a specific example, right? And so then this would be the incident angle in air. See how they flip, right? One's R over I, another one's I over R. They're flipping on us. So people don't like the confusing nature of that, so they redraw it as this, but there's a disadvantage there. We'll see in a second. Okay. The disadvantage has to do with the fact that there's lots of other stuff that has to do with index refraction, mainly wavelengths and speeds. So we're going to be doing that. So we're going to think of the fraction version of the equation. I think that's maybe the other reason we see that one in when optics used to be in grade 11. They had this one was used a lot because no one likes fractions. Anyways, moving on. So we also found that index refraction is like the wavelengths combined. Let me which way do I want to do this? I guess, yeah. Yeah, we can probably, I was going to develop that one, but I think we can just say the index refraction is also the ratio of the wavelengths. One way or the other here, I think I was thinking maybe we've thought of it more as the ratio of the speeds. Index refraction was basically like C over V, right? Like the speed of light over the speed in the material. I think that maybe is more familiar to you. Or you could say index refraction of the material. So let's call it like index refraction of let's just say, I don't know what you're going to call it there, but then this is index refraction of air or vacuum, preferably, but it's roughly speaking the same thing. And so we'd have the speed of sound, or speed of light, sorry, in air, and we'll have its diode, and the speed of sound in, oh, I did it again, speed of light in the material. Not talking about speed of sound here. Just rolls off the tongue. All right, so the true version is that we have like a 1, right? That's the idea there, that we have the 1. So these are the same thing. And so instead of C being in a true vacuum, you're like, okay, well, this is basically C, right? Anyway, so what I wanted to show, just to show why this works, is we know that V equals F lambda. And so we can say, oh, so then the index or refraction equals the wavelength in air times the frequency. Wavelength of light in air times the frequency of light in the air. And then we can have the wavelength in the material. So let's say, do you want to put an M on this, like whatever material we're talking about? So index refraction of a material. And then we have the speed in the material, index refraction of material, the speed of the material. Want to do that? And we have the frequency in the material. Any bells ringing here for you? And I could still show this as over 1, right? But we don't really need that if it's air or vacuum or whatever, right? So these guys match. Right? This stuff here and this stuff here match, right? So this is for air. No bells going off here as to what we could do. What do you know about the frequencies? What happens to the frequency of a wave as it travels from one material to another? Or should I say, what happens to the frequency of a wave once created in any situation?
It never changes?
Or it changes, that's right. These are the same. Right? Frequency never changes, right? So we can actually just cancel those suckers out. So we're left with that form that we were saying, like we are also know. So I just wanted to develop it for you to see, so you can see how that actually works, right? So this is the index refraction of the air over the material, or the wavelength in the air over the wavelength in the material. And again, this is the index refraction for the material. The wavelength of the materials in the bottom. All right. So if we know the wavelength is, the wavelengths divided is the index refraction also, as well as those signs of the angles, then we could, we could have this is actually developing the other way around, showing the rate of change of the velocity. So we have it both ways, but I think this is probably the way that is more appropriate, especially since it uses that frequency stuff's the same, but so did this one, so it's all good. Anyways, end result, index refraction for light going from material 1 to material 2. For example, air to glass, right? So we're going to remind ourselves that it's, it's the 2 over the 1, so that the glass over the air, right? But then it's equal to the air stuff, the 1 in the top. So the signs of the 1s, the velocities of the 1s, the wavelengths of the 1s, all in the top. So when you're working with Snell's law in the assigned work, you got to be careful to think about what direction we're talking about, right? And so if the refracted material, so this is the refraction material, the refractive material, and this is the incident material, right? So you could add that into the list as well if you want. Call the number 2 here the refractive material, and this the refraction angle, right? But I think that's what we've always said. It was like sine of angle I, right, over sine of angle R. That's what we've always said. And this was the index of refraction for the refractive material. So notice that this is, same as what we've always done. It's just we have these other versions kicked in as well, the velocities and the wavelengths, and also the reality that we're actually talking about another index refraction in here as well, right? So if this is instead of from air to glass, it's from oil to glass or water to glass, now we have the luxury, like the ability to actually calculate angles of incidence and angles of refraction and velocities and wavelengths and everything you want, even if we're not talking about air or a vacuum, preferably, to a material. Okay, because we can actually use this one, right? It's not always air. So it's not always an air or a vacuum, right? So this could be, something else. It could be water to glass. Because glasses right now that I'm wearing, and some people might be wearing, whatever. There's light going from air to glass, or it's actually plastic usually. But if you use your glasses underwater, refraction still happens from water to your lenses. So we should be able to analyze that, work with that. Okay, so that probably could be added to G2. Let's do that. I'm thinking of it. Equations somewhere in here. It won't be much longer. Goodness. All right, down here. Let's make a new page. What's that one there? Concentration momentum. Okay, we'll leave that. Let's go after that one. It's going to make a new page, but we should just add to this. Looks like I grabbed a little extra by accident. And yeah, so there's your full version of Snell's law, and got to practice being able to work with that. So let's look at that. So it says light with a wavelength of 6.5 times 10 to the 2 nanometers goes from air into ground glass. What's the speed in the glass? What's the wavelength in the glass, and so on. So I'm looking at this. Basically, what you do is you say, okay, there's my equation, and I'm going to use the index or fraction part because they're asking. Well, they gave us that information, right? And then they're asking for the speed in the first one. So you're using this part. So there's those two parts, right? So obviously you can just put numbers in and then calculate, or you can solve and then calculate, solve for the variable and then calculate. It's the same thing. Okay. So notice they said air into glass. Sometimes in the textbook they'll say let this be 1 and this be 2. I'd be totally okay with your statement here being like index refraction over index refraction and V over V, and having it be, okay, we're going air into glass. So this is the G, this is the A, right? Make that bottom one look more like an A. Less of a tail. Almost look like a G sometimes the way I write G's. And then of course you're like, oh, and then this is the 1 and this is the 2, right? So if instead of using 1s and 2s, you could use A's and G's for air and glass, just to help make it be less confusing. Because when I was doing these solution sets, I kept getting confused myself as to which one was which, the 1s and the 2s, which one did I call 1, which one did I call 2, and so on. Okay. Obviously, for the next one here, they are asking about the wavelengths. So really, we could have just done, so let's say then in B, you'd use this along with this, right? So the red and the red. So that's what I have here. Is that you could just use Snell's law again all over again. They're using the velocity that we calculated. Generally considered better not to use a calculation that you've done. So if this is part A and B in a test and you got part A wrong and then you're using it in part B, if your teacher is not as nice as me and at some point in a course, like I would take marks off here, and then here I would say, okay, well, you're using the velocity from there, and so everything you've done here is correct, and so I would mark it right. That's not always the case, especially if you have like a test that's all multiple choice. this is not the this wouldn't be the correct answer from multiple choice if this number was wrong from part A, even though you did all the right stuff. So compound errors, not a great plan. So I would recommend just starting with Snell's law again, right? Safer. Get one error causing more errors. So there's going to be work to do with that. Let's look at one of the solutions. Let's go with, oh, I gotta go over here, and we're doing lesson 53. Lesson 53. Craziness. Time flies. All right, so 53 homework answers. So what you're going to see as part of this work that I'm assigning, I just want to point out something that might not be as obvious until I sort of show it here, but that question we just did was to do with light, right? But there's going to be questions where you're going to be doing Snell's law to do with waves, like water waves, and then you're going to be doing Snell's law to do with light, and it doesn't matter. It just works. It's the same calculations, and I guess you sort of have to trust that it does work, but this is like experimental results agree with all of the stuff you calculate. So these two questions are to do with Snell's law to do with water waves. This one's to do with water waves. These are to do with water waves as well. Then this one's to do with light, like wavelength of light traveling from something to something. So you don't need to do all of these. I did all of them just so you have lots to refer to as solutions for practice. Okay, but you're going to be looking at Snell's law repeatedly, do at least several of each type for water waves and light, and you know, kind of be cognizant, if you will, aware. Think about the fact that you're doing Snell's law for light and for waves, and then you circle this, right? When you look at this and you say, okay, we're talking about whether it's a particle or a wave. To me, we need to kind of think, I think we need to recognize that we are saying that light is certainly behaving very predictably as a wave would, right? So that's like our, you know, gathering our evidence as we go. So the significance of what you're doing here is beyond just practicing and getting good at using Snell's law. It's also, you know, seeing for yourself that waves and light are very much behaving the same way. Okay, so that's so I was going to load up one of those. So let's look at these ones here. So this one is, I can tell they're giving index refraction for light. So you can see the way, you know, you're just basically doing the usual stuff. You might, like I said, you might want to sort of be obvious about what we're doing here for which to which. So this was index refraction for air into alcohol. And then that's why the alcohol one is on the top and the air one's on the bottom. But then, you know, if this is 2 and 1, then this is 1 and 2, right? So they flip. I just wanted to give you a little bit more coaching on that. But that one's to do with light. A lot of these are to do with light, and then you're going to get to ones where we're going to talk about the frequency of a wave here. Number 6, ratio of wavelengths. This stuff actually right here, page 450, sorry, is to do with water waves, like to do with waves itself. Whereas this one was to do with light. Okay, so when you look at the ones to do with waves, you might end up having to do some calculations to do with waves themselves, right? We have a frequency and we have a velocity, so we can calculate a wavelength. So I just wanted to point that out to you, that you're going to need that v equals f lambda stuff again, which we just reviewed recently, so it shouldn't be a problem. It's just in the context of a question. Seems like you're given a whole bunch of stuff and it's hard to know what to do, where to go, right? But you can see that link now between frequency and speed, of course, so you can get wavelengths and so on. And that comes up multiple times. There we go again. Oh, I gave you a frequency wavelength. Guess what? You can get a speed, so on. All right. So as usual, those are all ready. 53. Okay, so a couple other little phenomenon to do with light that we can say, oh, So light does it too, but we've kind of already done this, so it's kind of redundant. But we know that TV rock that I showed a long time ago, we have total internal reflection happening through the material. I didn't talk about, I talked about total internal reflection a little bit, but yeah, in that question earlier, it wasn't a full slide dedicated to it, or ever just sort of came up as part of it. This is just that TV rock, what it looks like. And so the writing sort of transfers like through and up to the top, like it's going through little, just a neat little thing. Anyways, so that is light totally internally reflecting. So we know that, of course, works, right? So then you're like, okay, well, does sound totally internally reflect? And yeah, it does. So as long as you're going from the slow medium to the fast medium, you can get reflections in sound even. Water waves, I haven't seen it. So we're looking at this usual debate here along the way. It's a bit of a question mark, I suppose, for water waves. I haven't. If you end up finding information about that, send it my way, because I'd be interested to see it. Did I skip a page? Double fraction. Looks like I must have skipped a page somewhere. Oh yeah, I did. That's why. I was like, I did have a page to do it. All right. I'll come back to it. But end result here, we're thinking like particle or waves. You know, maybe it's like, I don't know. We're left wondering, like, did we get total internal reflection of water waves? Is it matching that? You know, maybe only particles do that. As you're thinking through things. So just back to total internal reflection. I think we talked about this enough already anyways on that question. That we have to be going from slow to fast, right? So it must be, right? Must be slow velocity material to fast velocity material. That's a must. And of course, the angle of incidence has to end up being such that it makes the angle of refraction greater than 90, and so on. And there's that critical angle we talked about. So a little record of that. There's a weird effect of double refraction as well. This is calcite. So light refracting, and within this material, for some reason, it refracts things twice. End up with a double image. Oh boy, what happened? That's someone else's video.
이번 시간에는 평광판과
when I go to the full screen, it messes me up. Anyways, let's close some of that stuff. Oops, that's the one I wanted. Might have too much stuff open. All right, good enough for now. I'll just show it quick again here. Just go full size. Quicker. Maybe. So you see like the double image. You're not seeing double for other reasons. It's actually a double refraction. So there's pictures of it there, what that looks like. Anyway, so obviously refraction and total internal reflection and all that stuff happening with waves and light. Neat little application here. Polar bears, cute cuddly animals there, right? Nice and friendly. Their fur is actually basically clear. They're like porcupine quills, sort of, but not as spiky. And their skin is completely black. And I think we're running a little bit short on time here, so I'm just going to last time thinking about it, but are asking questions. But basically, that channels the light down into their black fur, absorbs the energy, keeps them warm. Kind of neat. So I think there's an article there about some kind of sweater that someone designed that would be like a polar bear thing to be warm. Interesting enough. Might have a black, like the inside of it's black, and then the fibers photo, like the light energy goes in. Obviously, we know about fiber optic cables, just reminding you of things that we've seen before. So just to reiterate here, you're probably not going to do all of those questions like I did, but you're going to do a bunch of water ones and a bunch of air, or a bunch of light ones, I should say. A bunch of air, where'd that come from? All right. Questions? All right. So we are continuing on this journey. It's just the next lesson. And I looked at the numbers again today, and we're still on track to just finish the course. So I don't have the luxury of saying, oh, we're good, we can take it easy, whatever. It's the curriculum is what it is. So we are starting to look at diffraction, dispersion, and partial reflection, partial transmission, which are wave things that we've seen before. Okay. So just recall what this means in the first place here. If diffraction happens, are we doing diffraction here? Yeah. So diffraction is when water waves spread out. And so you saw this before. I don't want to be redundant here and waste time, but yeah. So I'll deal with the diffraction specifically on that page. But basically, if light can be observed to diffract also, then it'd be pretty good evidence of light behaving and behaving like a wave, exhibiting wave properties. So that's one of the things we're going to talk about next. So diffraction, right? So that's the change in direction, or the bending, as a wave passes a barrier or goes through an opening. So we saw that in the wave stuff in grade 11 in a lot of detail. Looked like that, where passing an opening, you have these straight waves here, get this like big curve because of a change in direction. That's diffraction. And then obviously ending up looking like a circular wave as we went through an opening, all because of diffraction. Okay, so I'm just reminding you of the physical realities of diffraction. Some of the key points here were about the amount of diffraction. And so as wavelength increases, the amount of diffraction increases. In general, we're going to say that the wavelength, right, must be equal, but preferably greater than the width. Okay, so we're going to say like the wavelength has to be greater than or equal to the width, particularly the greater than idea, right? For some reason, they like to show it as the ratio of them is greater than or equal to 1, but doesn't help me understand the concept any better. So I suspect it doesn't help you. Okay, so the two things that you'd observe when you're playing around with how much diffraction happens is you find that as the wavelength increases, you get more diffraction. So if I'm increasing the wavelength of this, so making the waves be spaced further apart, then you get more bending. And then in this case, you find that this width W, as you make a smaller width, you get more diffraction. Put those two together, and what you're getting is like, oh, okay, I get it. This thing, the wavelength has to be bigger than the width. Okay, so that's what we remember and have seen before from grade 11, diffraction as a concept. So now we're doing the grade 12 stuff. So obviously here, wave properties as we just went through. Give me my screen back, you. All right, one moment here. Right, so right here, obviously we're talking about, you could talk about the, the Huygens principle. Huygens wavelets helped us explain how diffraction even occurs. The applet's not working anymore, but we know waves diffract, and we talked about the Huygens wavelets in the past, even as to help us understand why, right? That if these are made up of a bunch of circular wavefront crests that are all constructively interfering and forming a nice straight line, then when we disrupt that straight line addition of of them adding up, then you get the curves showing up, right? So we can explain diffraction nicely with waves. So Newton, good old Newton that he is, he's a little stubborn. He refused to believe that light diffracts at all. There was no way to explain diffraction with particles, right? So he said it doesn't do it. With quantum mechanics, we'll see later on, there actually is a way of explaining diffraction of particles. And so we will be coming back to that, okay? But basically, roughly speaking, in terms of tennis balls and golf balls and macro-sized particles, you can't explain diffraction. Like golf balls going through a gap in a fence don't spread out and look like they're coming from all directions, but it turns out light does. Okay, diffraction's not easy to see in nature. And the reason for that is because the wavelength is so small, right? The wavelength of light is extremely small, which means that diffraction isn't super noticeable. So let me view this here, entire page, which should have a big picture of what we're doing here, right? Or again, we're looking at diffraction and saying, okay, well, waves, certainly it's well explained, right? Waves are like, yep, diffraction's all good. So now we're thinking, okay, does light do it? If it does, then of course we've got a wave property of light that we can say, okay, now that's good evidence, right? So Newton tried hard, like basically Newton just refused to believe that it did diffract because he didn't at the time have any way of explaining it to his particles because he didn't know about quantum mechanics yet. The world didn't know about quantum mechanics yet. And it turns out it does. And so of course we're talking about evidence of wave nature of light. So back to bigger view for you here, get easy to see. Gravity, I'm surprised Newton didn't describe it, but gravity could have been used as a way to try and describe diffraction, right? If you had an object going through here and then there was a force of gravity, Fg, attracting it sideways, could make it have this new direction, right? I'm shocked that Newton didn't argue that, but it just turns out, of course, that gravity, it's not the cause. Gravity isn't strong enough to actually cause diffraction of light particles. So, if gravity had a strong enough effect on light, then, direct diffraction, it probably would be explainable with gravity. It just doesn't have anywhere near the strength necessary to make it observable in any case ever. So it's interesting. Surprised that he didn't argue that one and say, oh, see, I can even just explain diffraction, but he didn't know it existed, so that's why. So I want you to be able to see diffraction for yourself, and luckily I'm aware that all of you are equipped with the appropriate or necessary material. You have a finger and a thumb, correct? Still, last time I saw. Take your finger and your thumb, just like you see in the picture there, put it up to a light that's nearby you. Put your finger and thumb super close to your eye, looking at the light through your finger and your thumb. Bring your finger and thumb close together before your finger and thumb actually start to touch. What do you notice about the light that you're looking at close to your eye, your finger and thumb close to your eye, the light coming through between your finger and your thumb to your eye? What do you notice?
You can't see it anymore before they touch.
Before they touch, you get a dark, like it's almost like a wart. A former teacher I remember describing it as a wart grows from your finger to your thumb, and from your thumb to your finger. Firstly, like this little dark patch grows there before you're even touching, right? So we're looking at our thumb and so on. We observe this little dark patch, like grows. I even captured pictures of it. Little dark patch grows between your finger and your thumb, right? What's the explanation of that? What's causing that? That is, I believe, I'm going to skip ahead to the slide that describes this, right? But so what's causing that is that light would normally be going through the space to your eye, right? And it diffracts and changes direction and no longer arrives at your eye. And so the picture would look like this, right? Let's picture your finger and your thumb. I'm trying to think what this would look like here. Thumb has to be upside down, of course. So finger and thumb, and light would normally be coming through. Let's go with a blue ray of light here. Almost. There we go. So light would normally be coming through to your eye. All right, so let me draw an eyeball here like we always did. Whatever. Eyelashes. And so light would normally be going like that, but instead, because of diffraction, it gets deflected off into a different direction. So as it goes, because of diffraction, it goes like that, right? So it diffracts and it leads to, so it diffracts and eventually, it doesn't arrive at your eye. And so what are you going to see? If light's not coming to your eye, then you're going to see darkness, right? So the light diffracts away from your eye. And so, of course, you see darkness. You see darkness instead of light, right? So Newton didn't really need any fancy equipment in order to actually see that he was wrong, that diffraction actually does occur. I feel like I could change my angles here a little bit, but I don't think it really matters too much. Not too hard, so I'm gonna just show it like that. Right, there we go. Yeah, kind of neat, right? That you can see that yourself, and zoom in there, you can see it. This is a little video in case anybody's saying, oh, I don't see it, because sometimes that happens. No one's keying their mic and saying that though, but here's a video of it that I took this morning. That little...
My fingers don't actually touch there. They just get so close that diffraction diffracts the light away from your eyes, and you see a dark lump.
Right, you can see it jump. Little darkness jumps out between the two. Very, very, very easy to see. I found a video online too, but mine was, whatever, I made one afterwards, so you don't need to see both. Okay. Can you do it again for me? And this time just look at it like really carefully. Can anybody tell me any other details about that darkness in there? Do you notice any other details? If you're looking super intently at it. You got your finger and thumb fairly close to your eye. Do you notice anything other than just a dark lump growing?
It seems more like attached to the top finger.
Okay. Is there any patterns or anything else other than just a little, like I certainly think you're probably seeing, let me just 1 second here, I'll take your answer in just a second. I think you're certainly seeing this, right? So you're seeing, sometimes it does appear to be attached to one more than the other, whatever, but you're basically going to see like a lump like that, right? Like a dark lump like this in between. It almost has like curved edges on the side when I'm looking at it. So that, right? But is there any other detail in that dark lump that's growing? Someone was keying their mic. Go for it.
Yeah, I thought it kind of looked like a bunch of dark lines.
Yes. Okay. Yes. Okay. I cannot get a photograph of it. Okay. I tried. Even Kayla, I got her to try and tap the screen to focus on the right spot and everything else. There's little lines that are parallel to the surface of your fingers, and that's important. Okay. That's something that we're going to be able to explain why later on. That is going to be in our lesson to do with constructive and destructive interference. Those are nodal. That's a pattern of nodal and antinodal lines. So I hope you're kind of thinking cool at this point, because it is. Like it not only could diffraction have been noticed by Newton, he could have discovered, patterns of constructive and destructive interference with light. So as excited as I got when I was able to show constructive and destructive interference with sound, like the two speakers cancel each other out and it gets quiet, this is to me is equally as crazy, that you can actually see the interference pattern between the fingers. Okay, so this part here, the details in there, you actually get constructive and destructive interference of lights, and so you get these pattern of light and dark bands in those lines. I guess I already had it on this page, but you probably weren't looking there anyways. But yeah, it's a wave property, right? So again, we're saying, okay, we're looking at properties of light and trying to figure out what we're thinking it is. This is a huge piece of evidence for wave nature. Okay, yeah. Was anybody else able to see the little parallel lines there?
I couldn't see them.
No.
It just use glasses.
It is a bit tough. I have a little bit harder time now because in my advanced life experience stage, advanced age, I guess I can't see stuff close up as good. But I feel like you don't even need to really see it well. Like even if I take my glasses off, I can still see it, but it's better with my glasses though. Yeah, look at it through like a magnifying glass and so on. But I see the lines better when my fingers are a little bit farther apart than right together. Once you get them, anyways, give it a try. Maybe brighter light or different such situation, but this is a link to someone had asked or talked about it and so on. But that's what I'm indicating there is you zoom in and you see it, but it's redundant. I already talked about it enough. Okay, So of course we're saying like light diffracts. That's cool. So here's another example. Here's the sun being looked at. You know, there's a pole that's like blocking out the sun. But look at the light from the sun. You can actually see because it's diffracting and coming and hitting your eye when it shouldn't be able to. And so it looks like there's sunlight coming through the cement pole or whatever this thing was, like a telephone pole or something. That's diffraction. Okay? It's diffracting and able to come to your eye. This is called the Poisson disk. There's a person, a French mathematician that you know looked at diffraction and of light and showed. So he shined light at a disk and showed that there was a bright spot in the middle of the disk, which was due to diffraction. Okay. Details coming soon, but you'll see that bright spot in the middle, and then you'll also see an interference pattern. Okay, so that's details that we're going to be able to see soon, but it's just to see that this happens in everyday life as well is kind of neat. So this is a shadow from a sun, and then going through a screen window, and then landing on a leaf. And look what you see in the middle of the shadow of the screen grid. See those light bands in the middle? Those are the bright spots in the middle of the shadow because of diffraction. Okay, so that's a Google image. This is from the floor of my boat. This one, yeah, I believe is from the floor of the boat. Right, so this is, if you look super close there's a shadow line, and then in the middle of that shadow line, there's actually a light in the, you know, a light section in the middle of the shadow. And the only way to explain that is diffraction. So diffraction, yeah, light does this. So big piece of wave evidence. Okay, particles can't really be explained, but turns out with quantum mechanics you actually can. So with I'm gonna maybe modify this with quantum mechanics, you can explain diffraction. All right, just be right back. All right, sorry about that. I just had to take a fresh loaf of bread out of the bread maker. It smells delicious, by the way. All right, so dispersion, right? So dispersion is something we know that waves do, right? My screen. All right. So waves and light are observed to refract different amounts depending on the frequency. They're just observed to do this. Masses, what does it say? Not mass. So I guess over here I have to sort of look and say like Newton thought, so he saw this obviously, right? He saw this clear as day and he's like, okay, I have to be able to explain this. So Newton said, oh, maybe, you know, I wish he had said maybe it's because of, but instead he said, I declare it is because of the masses of the particles. He was a, you know, old school kind of thought guy, but just assumed he was right. But anyway, so he thought the masses of the particles were different, and that caused the different amounts of refraction. We're back to refraction, by the way, now, right? So this is back to refraction. Refraction instead of diffraction. If that makes sense, right? What part do I need to have? I don't want to just distinguish between the diffraction, right? So back to refraction, not diffraction. Anyways, so he said, oh, I think it's because it's the, you know, it is definitely because I said so, of mass. And so particles with more mass would have more inertia, and so they're not going to be bent as easily, you know. And then, you know, so is the red particle the more massive one because it's not bending as much, you know, is the idea, right? It turns out that it's not mass that's causing this. Particles of light are massless, and so it's not explainable based on masses. And so basically we're saying, okay, well, it's, obviously we're talking about a wave property at this point, that we can see that light disperses just like waves do. So I think we should pay a little bit more attention to this, why light refracts different amounts depending on the frequency. And, on top of the fact that waves do it, I suppose we don't need to analyze it any further, since waves do it for sure, right? It's just the way it is. We saw it in the past where we saw like waves coming in with a big wavelength coming into a boundary, and the amount of refraction they undergo literally just depended on the wavelength. So based on that, I suppose we don't need to analyze it any further. Just say light's doing it just like waves do. We can explain it a little bit more though if we want. So light, the idea of the interaction, right? So this is the textbook. I'm going to put it in quotes here. Explanation, and I'm saying in quotes there because there's times in textbooks where they gloss over things. I think maybe just to make the textbook not weigh as much in the end sometimes. But this paragraph, if you read it, it's kind of like it's pretending to explain things, right? But then you're left wondering like, but why? Why does the wavelength affect the amount of diffraction? It says, although wavelength does affect the amount of refraction, the behavior is the reverse of what we see in the ripple tank. So apparently it's the reverse of what we see in a ripple tank, right? So then like some more explanation is needed. Okay. So it turns out, I'm going to explain it up here, right? But they continue on later on. This textbook separates out, and they go through all the wave stuff, and then they go through all the light version of the wave stuff. And clearly I'm doing it simultaneously, so I'm bouncing back and forth between pages. You'll see in the homework from the other lesson. That's why I have pages in the 450 range, but then also pages in the 480 range, right? Because the wave stuff, purely wave stuff, and then the light version of it, we're tackling it simultaneously so that you can see the link between them. So if I was designing this textbook, I would have it like, merged together. Anyways, so later on, they're talking about, light refracting and so on. And they do admit here, they're like, we'll see later, the explanation is a little more complex, but he just says, like, they just say here, light's refracted because red, it's more because the red has different wavelengths. But with knowledge available at this time, this explanation is satisfactory, or was satisfactory, right? But like I mentioned before, it has to do with energies, right? So the index refraction is different for different frequencies, different wavelengths. Yeah, because the energy of the light is related to its frequency. Turns out that's the extra information that we don't have yet, but we are going to see that later in this course. In fact, we are going to, I suppose, see a video of the experiment. I'll have to go into the school and grab the stuff I need, but we can actually determine this H bar value. So you're going to hear about H bar for a while and learn about the significance of that value, the proportionality constant H bar. And then we're going to actually do an experiment to measure it. We can actually experimentally, but right now it doesn't sound as exciting because you don't know what H bar is. Okay, but H bar is a really cool thing, and we'll learn about it first and then even see that we can measure it. But long story short here, the higher energy levels interact with electrons in the atoms and the molecules more, and so of course it takes them the higher energy, it takes longer to get the higher energy stuff to vibrate as much as it needs to, so it slows down more. Okay, so higher energy light slows down even more, and so you get the high energy purple stuff refracting more, right? So that's right here, the high energy purple stuff. High energy purple refracts more. Ugh. Okay. What else do we need to do? Lots of wave stuff in this one, just reviewing ideas and just again collecting evidence, right, of the nature of things. So we're saying, okay, so it disperses. Yeah, there's another piece of evidence. of wave properties. Yeah, and so the high energy stuff has lower wavelength. That's the opposite part because it diffracts more, whereas the bigger wavelengths with water waves. So I should say, but it is reverse, right? Right. So it turns out that small wavelength light refracts more. So that kind of leaves, in my mind, that leaves a bit of a question mark, right? It's like, is that truly evidence of wave nature of light then, if it's the opposite of what we'd be expecting? So is this, is this really wave nature of light then, if it's the opposite direction? I'll leave that with you. So this one's funny. This one's funny. Newton. Okay, so partial reflection, partial transmission, right? So we know with waves do this, and then basically light does this very easily as well, right? So Newton couldn't deny this one. Okay, so this is, you're seeing through the window and you're seeing a reflection, right? You're seeing through windows and seeing a reflection. So you're seeing partial reflections and partial transmission. So you see the reflection, but you can also see the bottom of the pond or the fish underneath the water there, right? So partial reflection, partial transmission, super obvious, and waves do it. So we're like, yeah, sweet, right? Excellent wave evidence here since waves do this. Newton, wanting to defend his particle theory of things, couldn't deny this one because you can see it so easily. So he devised and published and promoted his theory of fits. His theory of fits, to quote unquote explain this, was that sometimes particles arrive at a transparent boundary in a fit of reflection, and so they reflect. And then other times they arrive in a fit of transmission. And so basically, if the light feels like reflecting, it reflects, and if it feels like going through, it goes through. Excellent explanation, right? I'm joking, of course. It's embarrassing that he said this. It's actually written in books, the theory of fits, and it's a little silly. But we know waves do this, though. Don't worry about the details of this, but we've seen this, right? We saw the pulse goes, even waves on a spring do this. A partial reflection comes back and so on. Like it's so obviously a wave property, right? Partial reflection, partial, I'm not getting you to do the details of this. I just included all the pages just for that. Even the video is there if you want to see them still. But waves do it. And so partial reflection, partial transmission, absolutely. This is a big one, right? This is an emphatic one. There isn't even any, but it's opposite or whatever. This one's like awesome. So if you're asked at some point to describe, properties of light that support wave theory or particle theory, that's what we're doing. We're collecting a bunch of yeses and nos or whatever for it. So far, I think the only one for particle in my mind was the gravity, I think, right? The rest are like wave. Questions about that stuff? All right, so there's less stuff here. This didn't take me as long to do these solutions. So I would definitely recommend being careful with this, and also, of course, do some of each of them. The ones with the waves, where you have frequency and wavelengths, so you have to get speed and vice versa. Make sure to tackle some of those in your practice. So there's still about almost an hour of official physics time. And then, of course, the usual 45 minutes that you do from each class. So unbelievably, based on our scheduling, it would be reasonable for you to spend like an hour and a half easily working on this. So, that's the amount of effort and work that should be going into this to achieve at a normal level in a normal semester. Just as a word of caution. Okay. So I will save these. I'll give you time to do that. I will stay near the mic here for quick questions. And that, I'll turn my mic off for now, though, so you don't hear my clicking, as always. And I'll remember to turn the video off, or recording off this time. What's that, Paige?
Is there going to be a meeting at 1 today?
Yeah, I can log in at 1 for you. Yep. Yep. All right, so let's remember to stop the recording.